Hello, welcome to another module in this massive open online course. So, today let us start looking at double sideband modulation. This is a different modulation scheme. It is a form of amplitude modulation termed double sideband modulation, also denoted by the abbreviation DSB. DSB stands for double sideband. Okay. In the double sideband modulation scheme, the modulated signal xt is described as follows: xt equals AC mt cosine 2 pi fct. Now, observe that in this amplitude modulated signal there is no pure carrier component, correct. We simply have the carrier that is modulated by the message AC, mt is the message signal, cosine 2 pi fct, carrier at carrier frequency fc. Okay. So, mt is your message signal, and this fc, as we have already seen many times before, this is the carrier frequency. Okay. Now, since there is no pure carrier, all right, this is also termed as DSB SC, where DSB, as you already know, this stands for double sideband, SC stands for suppressed, correct. SC stands for suppressed. And DSB stands for double sideband. DSB stands for double sideband, SC stands for suppressed carrier. Let us look at the spectrum of a DSB SC signal. Let us start by considering a typical spectrum of the message signal MT, correct. Typical signal message spectrum MF, this is the frequency axis, all right. In the frequency domain, this is the spectrum, MF is the spectrum of the message signal. Spectrum of the message signal, xt equals AC mt cosine 2 pi fct. Okay. I can write this as the product of mt with AC cosine 2 pi fct, correct. Xt is the modulated signal, correct. I can write this as the product of the message signal mt with AC cosine 2 pi fct. It is a multiplication in the time domain, which means the frequency response xf, right, is the frequency response mf convolved with the frequency response of the carrier AC cosine 2 pi fct. So, multiplication in the time domain is convolution in the frequency domain. Therefore, we have, correct, we have already seen this before. Therefore, xf is equal to mf, the message spectrum convolved with the spectrum of, so MT has spectrum MF, AC cosines 2 pi FCT has spectrum AC by 2 delta F minus FC, that is impulse scaled by AC by 2 and shifted to FC in the frequency domain, plus AC by 2 delta F plus FC, that is impulse shifted to minus FC and scaled by AC by 2. So, this is the spectrum of AC cosine 2 pi FCT and convolution MF, alright. So, just MF convolved with delta F minus FC, that is alright, that so it is AC over 2, MF convolved with F minus delta F minus FC is MF minus FC, that is spectrum of MF shifted to FC, plus AC by 2, MF convolved with delta F plus FC is spectrum MF shifted to minus FC, that is MF plus FC. Okay. So, this is the spectrum of the DSB SC signal. This is the spectrum of the double sideband suppressed carrier signal. This is the spectrum of the DSB SC signal, correct, which is XF, that is AC by 2 MF minus FC, that is spectrum MF shifted to FC scaled by AC by 2, and AC by 2 MF plus FC, that is spectrum of MF shifted to minus FC and scaled by AC by 2. Alright. So, let us now describe this schematically. I can draw this. So, I have at FC, alright, I have FC, this is FC plus FM, FC minus FM, correct. If the maximum frequency component of the message signal we denote it by FM minus FM to FM, correct. And then what we have is, we have this point will obviously be half AC M of 0, that is a spectrum at 0, because this point, remember this point is M of 0. So, this point is half AC M of 0, correct. M of 0 is the spectrum at f equal to 0, correct. This is basically your AC by 2 MF minus FC. Correspondingly, on the negative, we will have an image of this on the negative frequency axis, correct. You will have an image of this on the negative frequency axis. This is minus FC minus FC plus FM minus F minus FM, correct, correct. So, this is the image, and this is the, and this is basically corresponds to AC by 2 M F plus FC, that is the spectrum MF shifted to minus FC and scaled by AC by 2. Alright. So, you have two bands, one from FC minus FM to FC plus FM, and the other from minus FC minus FM to minus FC plus FM, and as you can see, there is no pure carrier component. That is, unlike the conventional AM signal where you had impulses denoting the pure carrier, there are no impulses, which means the pure carrier component is absent. You only have the carrier that is modulated by the message. Okay. So, this is the spectrum of the DSB SB signal. So, let me characterize that. So, this is the spectrum this is the spectrum of the DSB SC signal. Let us now look at demodulation of the DSB SC signal. the demodulation of a DSB SC signal, and for demodulation we can multiply it again by the carrier, which is also termed as a coherent carrier. I am going to explain this later. So, demodulation can be carried out by multiplying by a coherently generated carrier cosine 2 pi f c t at the receiver. Okay. So, demodulation can be, let us note that down, demodulation can be carried out by multiplying with a coherently this is an important term, coherently generated carrier cosine 2 pi f c t at the receiver. So, demodulation can be carried out multiplying by with a coherent carrier cosine 2 pi f c t at the receiver. Let us look at that. So, let us look at our signal x t at the receiver. We can express R t equals x t demodulate with the coherent carrier, that is cosine 2 pi f c t, which is equal to A c m t cosine 2 pi f c t times cosine 2 pi f c t, which is basically, you can write this as A c m t cosine square 2 pi f c t, which is basically your A c. Now, cosine square 2 pi f c t can be written as 1 plus cosine 4 pi f c t divided by 2, alright. Cosine square x is 1 plus cosine 2 x divided by this, cosine square theta is 1 plus cosine 2 theta divided by 2. And now, you observe something interesting. I have A c m t divided by 2 plus half A c m t into cosine 4 pi f c t, and if you observe this, this is cosine 4 pi f c t corresponds to a frequency, that is, the frequency is equals to f c. This is of course your baseband, that is centered at 0. This is at frequency 2 f c. So, this is centered, this component, if you can look at this, this is centered because of the cosine 4 pi f c t, this is centered at 2 f c, alright. So, we have two components, one is A c m t divided by 2, which is in the baseband, which is m t scaled by A c by 2. So, naturally it is in the baseband, that is from minus f m to plus f m, correct. However, m t multiplied by cosine 4 pi f c t, cosine 4 pi f c t has frequency 2 f c, which means it is the spectrum of m t, that is m f shifted to 2 f c and minus 2 f c. So, this is far away from the baseband, alright, and this component can be removed by filtering to recover m t. So, let us look at the spectrum to understand this better. Let us look at the spectrum. So, the spectrum of this, that is R t equals x t cosine 2 pi x t multiplied by the coherent carrier, and if I look at the spectrum of this, that is R f, I can draw it as follows. Look at this, R T equals half AC MT plus half AC MT cosine 4 pi FCT. The spectrum of this half AC MT has the spectrum half AC MF plus, of course, I have MF convolved with the spectrum AC divided by 4, because I have MT multiplied by AC over 2 cosine 4 pi FCT, which means in the frequency domain it is spectrum MF convolved with the spectrum of AC over 2 cosine 4 pi FCT, which is AC over 4 delta F minus FC plus AC over 4 delta F plus FC, which is equal to half AC MF plus AC over 4 MF minus FC plus AC over 4 MF plus MF plus, I am sorry, MF plus, this has, these are components at 2 FC, I am sorry, cosine 4 pi FCT has components at 2 FC. So, this is AC over 4 delta F minus 2 FC plus AC over 4 delta F plus 2 FC. So, this is AC over 4 MF minus 2 FC, AC over 4 MF plus 2 FC, and therefore, naturally when I draw the spectrum of this, I am going to have the baseband component, correct, that is your half AC MF, that is going to be there. This point, this is your half AC MF, this point is half AC M0, and then you are going to have, so let us say this is FC, you are going to have bands at 2 FC, that is side bands at 2 FC, and so this is at 2 FC, you have a component which is basically this component is your half, or rather 1 over 4 AC MF minus 2 FC, and similarly on the other side at minus 2 FC you are going to have another component which is basically at minus 2 FC. So, this is your 1 over 4 AC MF plus 2 FC, correct. So, you have these two bands at 2 FC and minus 2 FC, and therefore, now I can have a low pass filter, correct. I can have a low pass filter because there is base band is separated from the side bands at minus 2 FC and FC. I can now have a low pass filter. I can now pass this signal through a low pass filter, that is minus W to W. This is a low pass filter. this is your low pass filter, and these are the side bands, correct. These is the base band and these are the side bands at minus Fc and 2 Fc. Side bands at minus 2 Fc comma Fc, and the base band, that is AC over 2 MF, this can be separated from the side bands by passing it through a low pass filter between minus W and W, and W can be chosen appropriately, alright, because there is significant separation, alright, because FM is much, that maximum frequency FM is much less than Fc. So, naturally maximum frequency FM is much less than 2 Fc and it is much less than 2 Fc minus Fm. So, if you can see, there is a significant separation, correct. Here if you can look at this, there is a significant separation. So, choosing a low pass filter of bandwidth W LPF of bandwidth of, let us say, suitable bandwidth, let us make it suitable bandwidth W AC over 2 MT can be separated from AC over 2 cosine 4 pi FCT, correct, because this is your base band, this is in the base band and this is actually, these are the side bands at 2 Fc comma minus 2 Fc, and the LPF, the low pass filter, correct, low pass filter is chosen such that, choose LPF such that cutoff frequency W, that is we must have Fm. Now, if you can look at this, that is very interesting, you have Fm should be less than 2 Fc minus Fm, that is we should have Fm less than equal to W less than or equal to 2 Fc minus Fm, and this is possible, this is possible because we have Fm, that is maximum frequency component, much less than or equal to Fc, which means 2 Fm much less than or equal to 2 Fc, which means, which implies automatically that Fm is much less than or equal to Fc minus Fm. So, this because Fm, the message frequency, is much less than or equal to the carrier frequency Fc, this is indeed possible, and therefore, you can choose an appropriate cutoff frequency W of the, this W is termed as the cutoff frequency, alright. So, that is the cutoff frequency of the LPF. One can choose the cutoff frequency of the LPF appropriately, right, such that it is much greater than Fm, much less than 2 Fc minus Fm. So, the LPF blocks the blocks the side bands at minus 2 Fc and 2 Fc. So, the LPF, basically LPF blocks the component cosine 2 pi fct mt by 2 cosine 4 pi fct, this is the component at two fc, right. The carrier has a frequency, a cosine corresponds to cosine 4 pi fct corresponds to the frequency 2 fc, alright. So, in this module what we have seen is we have seen a new form of amplitude modulation, that is double sideband modulation, which has no pure carrier, does not transmit the pure carrier, therefore, it is also known as DSB SC, double sideband suppressed carrier, alright. We have seen the spectrum of the DSB SC signal and also how to demodulate the DSB SC signal by multiplying with a coherently generated carrier cosine 2 pi fct at the receiver, and finally filtering using an appropriate filter, low pass filter with an appropriate cutoff frequency W, such that you retain the baseband component while filtering out the side bands which are at -2 fc and fc. So, we will stop here and continue with other aspects in the subsequent modules. Thank you.